So, when you're in a stats class, you always hear about that perfect theoretical bell curve, right? But what happens when we step out of the textbook and into the real world? Well, today, we're going to bridge that exact gap. We're taking this super powerful concept of the normal distribution and actually applying it to solve real-life design problems.
I mean, have you ever really thought about it? How tall is your shower head and why is it that tall? Or what about the doorway you walk through every single day? It's definitely not a random guess. These dimensions are all about careful statistical thinking, and they're designed to work for almost everybody. We're about to pull back the curtain and see exactly how it's done.
Okay, here's our game plan. First, we're going to look beyond that perfect standard curve to see how data actually behaves in the wild. Then, I'll introduce you to an awesome tool called the Z-score. After that, we'll put it all to the test with two case studies, shower heads and doors. By the end of this, you're going to have a brand new toolkit for tackling these kinds of problems yourself.
All right, first things first, we need to get real about the data we actually encounter day to day. You see, that standard normal distribution from the textbooks, it has a perfect mean of 0 and a standard deviation of 1. But you know what? Real-world data is almost never that clean.
Think about it. Whether you're measuring the heights of adults, the weight of a product coming off an assembly line, or even a batch of test scores, they almost always form that classic bell shape. But here's the thing. Each of those data sets has its own center, its own average, or mean, and its own spread, or standard deviation. And all that variety creates a challenge. How in the world can we compare them using one consistent method?
Well, the solution is this beautifully simple yet incredibly powerful tool, the Z-score. I really like to think of it as the universal translator for data. It lets us take any normal distribution, no matter its mean or standard deviation, and translate it into one common language we can all understand.
And this visual just shows it perfectly. On the left, that's our real-world data, our non-standard distribution. Then that arrow in the middle, that's the Z-score formula doing its magic, transforming it into the standard normal distribution you see on the right. And here's the really cool part. Notice how the shaded area, which represents probability, stays exactly the same. All we're doing is changing the scale on the bottom axis.
So here it is, the formula itself. To get the Z-score, you take your data point, which is x, subtract the mean of the whole data set, that's the Greek letter mu, or mu, and then you divide all that by the standard deviation sigma, or sigma. Put simply, a Z-score just tells you exactly how many standard deviations away from the average your specific data point is. That's it. All right, that's enough theory. Let's get our hands dirty and put this tool to work. For our first case study, we're going to figure out what percentage of men might find a standard issue shower head just a little too short. The process is super straightforward, just 3 steps. First, we're going to visualize the problem. Second, we'll do our Z-score conversion. And third, we'll find our answer. Let's get to it.
Step 1, we sketch it out. The data tells us the average height for men is 68.6 inches, and our shower head is fixed at 72 inches. So what we want to find is the proportion of men who are taller than that. That means we're really interested in that little shaded area way over on the right side of the curve.
Step 2, we calculate. We just plug our numbers into the formula. Our x is 72, the mean mu is 68.6, and the standard deviation sigma is 2.8. A little bit of math, and we get a Z-score of 1.21. What this really tells us is that a height of 72 inches is 1.21 standard deviations above the average height for men.
And finally, step 3. That Z-score of 1.21 corresponds to a probability of about 0.1123. Now, the interpretation is what's key here. This means about 11.23% of men are taller than this 72-inch shower head. If you're a designer, that's a big deal. It means more than 1 in 10 of your male users are going to have to duck.
That was awesome, right? But what if we flip the problem completely on its head? What if we start with a goal? Like, say, designing something to accommodate 95% of people, and we need to find the specific measurement that gets us there. This is what we call working backwards.
Now, before we jump into our next example, here are a few pro tips to keep in mind. First, always, and I mean always, sketch a graph. It helps so much. Also, don't mix up Z-scores, which are distances along the bottom, with areas, which are probabilities. And remember, any Z-score to the left of the center mean is always going to be negative.
To solve these backwards problems, we just need to do a little algebra on our original formula. If we know the mean, the standard deviation, and the Z-score that matches our target probability,
we can solve directly for x, the exact data value we're trying to find.
So let's apply this new approach to our second case study, door design. It's a pretty common industry standard to design things like doorways so they can accommodate at least 95% of the population. So the question is, how tall does our door actually need to be? Let's check out the setup. The average height of all adults is 66.2 inches, with a standard deviation of 3.8 inches. Our goal here is to find the height x that separates the shortest 95% of people from the tallest 5%. We already know the area we want, that big 0.95 shaded region. Now we just have to find its boundary on the right.
Okay, let's be real. In practice, you'd probably just use a tool like Excel. Its norm.inv function is built for exactly this kind of problem. You just feed it the probability you want, 0.95, along with your mean and standard deviation, and boom, it spits out the answer, approximately 72.5 inches.
But it's so important to understand the math that's happening behind the scenes. So first, you'd find the z-score that corresponds to that 95th percentile mark, which happens to be 1.645. Then you just plug everything into our rearranged formula. And look at that, we get the exact same answer, about 72.5 inches.
So what does this actually mean in the real world? Well, our calculation says we need a door that's at least 72.5 inches tall to hit our 95% goal. But if you look at the International Residential Code, it requires doors to be 80 inches tall. So the verdict is clear. The standard 80-inch door doesn't just meet our goal, it easily exceeds it.
So let's just recap everything we just did. You've now mastered two fundamental skills that are really the core of applying normal distributions to practical, real-world problems. Think of these as the essential tools in your new statistical design toolkit.
And here they are. Skill number 1, going from a specific value, like a shower head height, to find a probability, using our classic z-score formula. And skill number 2, going from a probability, like a design requirement, back to a specific value, using that rearranged formula. With just these two skills, you can tackle a huge range of design challenges.
You now have the framework to analyze and design products and spaces for basically any population, as long as you have the data. I'm talking about everything from desk heights to airplane seats to clothing sizes. So, now the question is, as you look at the world around you, what would you design next?